So I've just finished my PhD, sort of a joint programme between UCL in London, which is where I did most of my work, and Asymptote. It was a industrial studentship from the MRC, and I'm just sort of going to maybe almost give two short talks, sort of summarise what the aim of my PhD was, what the conclusion was, and then sort of some interesting data that I got that I thought would be quite good to share, and perhaps any of you had any suggestions of what was going on. So I'll just load it up now. So I was working with a group with Barry Fuller, looking at the bioartificial liver. So what this is it's a device that has about a 2 litre biomass, and I don't know if this is perfect. So here's sort of an example of what it looks like in this 2 litre biomass. Is quite spread out. So these balls are about 0.5 millimetre across, and inside all the dark areas are clusters of cells. So each of those cells are liver cells, and they're clusters up between 200 or 300 cells. These are some that have been grown up, so they're quite cell dense. I've got some other ones in there that are less cell dense. We sort of culture these in a static layer culture. We then encapsulate these into the alginate, and then culture them for a further 12 days. And by that point, we have sort of sufficient biomass in this device. And the point of this device is it's going to be hopefully a treatment for acute liver failure. So if you come in to the hospital and your liver's failing, you'll be hooked up to this machine. This machine will take over the liver functions, which will give your own liver time to recover inside your body. It can have a break, and because the liver recovers so well, after some time you can be taken off the device and hopefully you'll recover without need for transplants. And at the moment for acute liver failure there aren't any treatments apart from having whole transplants, and if you have a transplant with acute liver failure you have a lower recovery on average than transplant for other procedures. There's also not enough organs around and immunosuppressants, so you really want to avoid that. So it takes us about 26 days to prepare one of these things from scratch. We culture them for 2 weeks in a sort of static culture, so just on tissue culture plates, and then we will encapsulate these into the alternate balls and grow those for a further 12 days. But one problem with acute liver failure is you sort of can die within 1 week to 4 weeks of the start of symptoms. So if you have to wait 26 days and you can get in a week, that's not really a viable treatment. So what we want to do is find a method where we can try to preserve this volume and then recover function within 72 hours, and that will give the doctors enough time to say this person needs the treatment for acute liver failure, and then get them prepared for the procedure. And then also I sort of went to look at wider benefits of cold temperature in liver cells, and that's sort of the second part of my talk today. So I'll just sort of say what previous work I did sort of during my PhD and also done before my PhD, and then I'll focus on today the cryopreservation of the 2 litre biomass volume. So a lot of work done in the past. I think a lot was done by Isabel, who's here today, on sort of smaller cryovials and then sort of in flat bag preservation. So they could cryopreserve these things sort of generally quite slow cooling rates, about 0.3 degrees a minute, and then if they warmed them rapidly, so put the cryovials, say for example, into a hot 30-degree water bath, you could have quite good recovery and have recovered within up 2 or 3 days post-thaw, as what the function was beforehand. I also, during my PhD, I developed a scaled-down process, so I'm not going to go into this in detail today, but the difference between ice forming on a small system is very different than a large system. In a large system, you have ice sort of growing much more slowly through the system. The whole sample won't supercool, just the edges of it. You have nucleation close to the freezing point, and a very different ice structure. And one of the limitations of the work I was doing here is we wanted to have the chamber that we could culture the bioartificial liver in during the growth phase, the same one that we could cryopreserve it on, so that when treatment started, the people at the hospital could just take the device, thaw it, and then hook it straight to the person and not have to worry about having a GMP facility and transferring sort of from a freezing system to the use system. So there's not really been a huge amount of cryopreservation in sort of large volume mammalian systems. So the largest volumes that you really look at are 100 to 200 mils in a cryo bag, but cryo bags are very thin and flat, so you have good thermal transfer through them. That's not the case for our system, which is essentially a cylinder which have up to sort of 7 centimetres of biomass sitting in. And also, a lot of the previous work on particularly liver cells, but also mammalian cells in general, they have different optimal cooling rates, but most warming protocols just say you have to warm very quickly. And there's not actually that many studies sort of looking at cooler warming rates and faster warming rates, And I think a lot of the reason behind using faster warming rates is just to have a cryovial. It's just easier to chuck it in a water bath, wait 5 minutes, and then go and put it in the system. That gives you a good outcome. That's good enough. But for our system, we couldn't really use fast warming rates because of a 2 litre volume. It was quite a thick, it was 3 millimetres polycarbonate, which is a very poor heat conductor. It really wasn't possible to warm it from minus 200 degrees to being thawed within sort of 5 to 10 minutes. So the first thing I really looked at is, well, how important is the warming rate? And the few studies that exist that look at different warming rates is how they test warming rates is they'll have a fast warming rate, which will be a sample in a water bath, and then the other end of the spectrum they'll have a slow cooling rate, and that can be, for example, they'll have a cryovial and they'll go and put it into a fridge. But really those aren't fast and slow warming rates, because even with a cryovial that you take out of liquid nitrogen and put into a fridge, you'll still have for the first 100 degrees it will warm incredibly rapidly because the sample's small and the fridge is 200 degrees warmer. So what you'll see is really the warming is really focused towards the end of the warming profile. When it's melting, it's say minus 4 degrees and the fridge is only plus 4 degrees, you've only got a sort of 8 degree temperature difference. So that's really where in a slow warming profile, such as putting your fridge, most of the warming profile takes place. So what I did with these samples were, here's the sort of the viability, and this is the viable cell number, is I got some samples that were stored at minus 80 degrees and then just in a controlled rate freezer I warmed them very slowly, just 1 degree a minute, and some of the samples when the chamber reached minus 40 degrees I took them out and put them into a water bath. On another set I kept them warming slowly until minus 10 degrees and then I warmed them rapidly in a water bath, and then the final set here were ones that I just warmed slowly all the way to 4 degrees, so just 1 degree a minute. And what I found was that for our liver cells at least, all that really seemed to matter in the warming profile was actually the very last stage of it, so the melting phase. So actually the warming profile didn't matter between minus 80 degrees and minus 10 degrees. You could do it quickly, you could do it slowly, there wasn't a difference between the sets. The only sort of significant differences in viable cell numbers, you got a drop from around, in these samples, 10 million cells per mil down to about 7 million cells per mil if you went through the phase transition process very slowly. So we found that was quite promising. So what that meant for our artificial liver device is we could just take it out of its storage temperature and we could just warm it very, very slowly, just moving it literally between different fridges and different freezers, different temperatures, and then just focus on trying to warm it very quickly through the melting phase. And it's much easier to warm something that's minus 30 degrees than it is at minus 200 degrees. It'll warm more rapidly. So here's the warming profile I used. So I had the chamber. We actually had a total of 2.3 litres biomass in this experiment. We had a bit extra, I thought I'd try more. And we had 600 millilitres supernatant. We found that actually having about 25% supernatant was also quite important to get good post-thaw recovery. I'm not sure if we've got time to go into detail about that at the moment. So the first stage was just a 2-hour warming phase, and I took it out of liquid nitrogen and I put it just into a minus 80 degree freezer. I then put it into a minus 30 degree freezer, and then in the final stage for another hour I put it at stage 3 into a planar control rate freezer at minus 10 degrees. And then when it reached about minus 35 degrees, I then took the sample out and then warmed it rapidly, and by doing that I just opened up the chamber, knocked out the biomass and poured warm media on it and hoped the thing melted. It still took about half an hour to melt at that stage, so it wasn't rapid warm, but when I'd done it in the past with just a mimic device, warm it directly from minus 200 degrees was taking 2 hours to warm it directly, so we managed to cut the melting phase from about 2 hours to 30 minutes, and that could be improved further. And here's sort of the results of this 2.3 litre biomass that we did in one sample. So on the right is the viability results. We see sort of early on the viability is quite poor, but by the time we get to around 72 hours of these post-thaw, the viability is above 90%, and that's what I defined as success. And then it sort of recovers fully by the time you get to 5 days post-treatment. And when I say viability, what I was measuring was, it was a PI FDA staining process, so the pyrimidine stained any dead cells, or any cells that had a permeated cell membrane, and the FDA was a metabolic activity, so the metabolic activity in the cells, they would dye yellow and then green, then I would just compare the fluorescence between those two images. On the left is the viable cell number. So originally the crab preservation started about 30 million cells per mil, And you see by the time we get early on, we've lost a lot of cells, and much more so than you'd expect from just looking at the viability. Not only are a lot of the cells dead, a lot of the cells have just disappeared, sort of intercellular transformation happening, just sort of destroyed the cell and the nucleus, and they get washed out, so the cells aren't there. So the cell number here was sort of just under about 20 million if you take into account the low viability. This is the cell count times viability. But then they recover by about 72 hours to the peripheral value. And this is a combination, I think, between cells that have a permanent cell membrane, so we're defining them as dead, having the cell membrane recover, so these cells recover. Also, there's cells starting to proliferate quite early on in the process, so they sort of reproliferate. And then by the time we get to 3 days, we have the level we froze it in, which was sort of our aim. Now, if you want to have the treatment, you don't have to wait 26 days for the treatment. You can crab preserve this device and then have it within 3 days of treatment. I also wanted to test some of the protein production. So really, with the artificial liver, we don't really care too much about what the viability is. We really care about are the cells producing proteins that your liver would produce, because we really want it to. We want the cells not to necessarily be alive, we want them to be producing as well. So here's looking at sort of the protein production. So in this slide here on the right is the performance per mil biomass. So that's, we freeze 2 litres, and this is how much on a volumetric basis they're producing. You see very early on they're very, very poor, producing almost nothing, and actually some of the proteins decaying. This is alpha-fetoprotein I was testing here. And then by the time we get to 72 hours, we can see actually we're producing more proteins on a per mil basis than we were before the process. So that is indicative that the cells are not only recovered viable cell number, but are in fact producing the proteins we need them to produce to be a viable device. On the left-hand side is per million cells, and this gives us a better insight into how healthy the individual cells are. And as you see here, by 72 hours, they're actually recovering quite well and are producing a lot more proteins than they were beforehand, and that sort of settles down. By the time you get to 4 days and 5 days post-treatment, they are producing around the same level of proteins per cell than they were when we were culturing them. So that sort of concludes that they were producing the protein. Also, I'm not showing the data now for time, but they were consuming glucose, they were had good MTT viability, they were producing lactate. So I did quite a large range of tests to see not only have we got the viability of protein, but are the cells producing most of the things that we want them to do. But also what I wanted to do is see, is there a way that we can improve this further? Can we cut down the process? So in this graph here, the black line, this is the data I just showed you, the viable cell number of the ones that were done in the large volume, the 2.3 litres. The light blue is samples I just crab preserved in cryovials, so I just cooled them at 0.3 degrees a minute, which they fill these samples, and then warmed them very rapidly in a water bath. And you see they did recover more quickly, and they were significantly better at 24 and 48 hours. The stars here indicate significantly better than the large volume. But the problem with the cryovials is we can't do the very rapid warm rates and very rapid cooling rates, so it's sort of it's a baseline, but it's not something that we can actually copy into the large volume. But what I did notice, if you look at the darker blue line, these are ones that I did in scintillation valves in a scaled down process. What I did is I mimicked very accurately on a smaller scale the conditions that are experienced in the large volume during cooling. So they've had the exact same cooling profile between these two sets. But these ones were warmed very rapidly, so they didn't have a half hour of melting. They had, I think it was 5 minutes and 30 seconds of warming, which was sort of the fastest we could do it. So I think in future, if we had an even better warming profile, so for example, if we had maybe like some sort of thawing device, if we had magnetic nanoparticles, some sort of there's a lot of data about potential ways of improving the warming profile. I think ultimately, if we did manage it, we would have recovered viable cell number and also protein production, that I tested as well, within 48 hours, not 72 hours. So that would further shorten the time between needing a device and having it available. And that sort of concludes roughly that section. So I think the main reasons I actually managed to do this crab preservation, which was I realised that we didn't need to warm it rapidly at all. All we needed to do was just melt the ice quickly. And the theory I had behind that, or the hypothesis, I haven't it's very difficult to test. I think there's a lot of refreezing goes on, so that, as you know, that when ice melts, it doesn't melt everywhere. There'll be sort of local areas where ice is growing, there'll be areas where ice is melting, and perhaps there's some sort of, as the ice is melting slowly through it, cells may experience ice melting, there may be a bit of regrowth, and that may damage the cells a bit. And also I did find that I needed some excess medium. When we had low excess medium, so say the biomass was sitting at 2.3 litres, and if we had only maybe 10 mils above it, you'd have a lot of crowd concentration in that top area, and also then you'd have a very non-equilibrium cooling profile as the ice was moving through. But I found if we added a bit more excess, even though the volume was bigger overall, that helped, and we did get recovery within 72 hours. So I think that we can sort of prove the concept that the biofilter liver device can be crowd preservable, and the treatment time for this device can now be cut quite considerably. And now I'm going to sort of almost go into a second talk, which sort of based on data I got there, and I thought it would be quite good to discuss here today in case any of you had any hypotheses about exactly what process was going on here. So when these cells are cultured, we culture them for the final stage when they're encapsulated for 12 days in a bioreactor. And what we generally see the profile is very roughly at the beginning we encapsulate them around 2 million cells. They grow quite rapidly, and then by the time they get to day 11, day 12, they reach around 30 million cells per mil. It varies experiment to experiment. Then they stop growing at that stage, and if you try and grow it for longer, the cells actually start dying off. So we can't really get above 30 million cells per mil. But what I've noticed, this is just the viable cell number graph I showed the large volume earlier on, is we get it to around 30 million per mil, which is what this one crowd preserved at. But after that stage, they still continue growing. By the end of the process, we had over 50 million cells per mil. So I was wondering, well, that's quite strange. Why are the cells growing to a higher cell density now than we were beforehand when we couldn't do it? So I wondered, is sort of the freezing or the cooling doing something either to the cells or the alginate that may somehow boost their cell growth? So what I tried to do to test this, when we encapsulated the cells, so when we just first made the cells before the culture period, I did sort of 3 different conditions between different experiments. So the standard one is to just add them straight to a culture flask and then grow them for 12 days, and that's how they're sort of growing on the smaller scale of standard in the lab at the moment. But I did sort of some more sets where what I did is, before doing that, is I just I had them in cryovials, all sets, and I just put some of them into a ice bucket and left them there for 45 minutes, and then I just go and put them into the culture flask. And then another set, what I did is I cryopreserved them as normal, so I added the DMSO and the Viaspan, cooled them, thawed them just as soon as we encapsulated them before they'd grown up, and then cultured them for between 8 and 12 days. And then I did viable cell numbers and a few other protein assays after that point to see what they were doing. And this is the data I got. So the grey line here is these are the ones that were just sort of the control ones, the samples that I put just into the T175 culture flask without doing any treatment to them. And sets A, B and F, I'm sorry about having those back. So these ones, these were cryopreserved ones. These ones I cryopreserved on, as soon as we encapsulated them, then I grew them for 12 days. A, B and C, and they were all significant. So the star is a p-value of 0.01 and the cross is 0.05, and they had significantly better function 12 days after treatment and cell number. And then the other sets, so C, D and E, these are ones that all I did to them was, before reculturing them, as I took them, I put them for 45 minutes at 0 degrees in an ice bucket with water in it, and then recultured them and no further treatments to them. And 12 days after treatment, they were all significantly better than ones that I just put directly across into culturing, which was this is sort of 6 different experiments, n equals 5 per set, so we've done this quite a few times. And here's sort of what happens in a more detailed scale. So the light blue line here is the control samples, this one here. So, and the black line are ones that were cryopreserved. So the cryopreserved ones, you see, they tend to, this is the day 0 thawing for these ones, they have much poor function coming out for about the first sort of between 5 and sort of 8 days post-treatment. But then after about a week, their proliferation really boosts at that stage, and then they boost up to, in this stage, 40 million cells per mil, whereas the ones that were just control ones, we had they were better for most of the culture period, but then when they boosted, they didn't boost to quite the same level, so we had about sort of half the viable cell number after that point. which may be why this has been missed in the past, because normally for post-thaw I will sort of compare day 1, day 2 and day 3, and doing sort of day 1, day 2 and day 3, the cryopreserved ones were always worse viable cell number than the control ones. However, when we did this out to the 12-day culture period, and we did the 12-day culture period because that's how we normally grow the cells, we had quite a higher viable cell number, which was very surprising. So I've tested quite a lot of reasons behind this. For the ones that were cryopreserved, I tested, is it just the via spanner we're using, is it the DMSO? I've tested them all on their own and as mixtures, but that didn't have a major effect, and the ones I just chilled didn't use any cryoprotectants at all. I've checked the chilling times, so you doing it between sort of, say, short as a minute or having up to 90 minutes, there wasn't a significant difference between the growth in all of those sets. I tested the cooling rate, so I sort of between 0.3 degrees a minute, so one's cool fluent AF600, and samples that I just injected directly into a chilled culture media, so almost instant cooling, didn't seem to have an effect. So what we did see when we looked at the function is the function on a per cell basis was lower, so they're producing more proteins and tend to be producing less MTT. For around 9 to 12 days post-culture, so the protein production, so the production of the cells is actually much lower. Part of this, I think, is due to the fact these cells are proliferating more, so when they're proliferating, they're putting more resources into growing and, as opposed to producing proteins. But in terms of actually using the system, we want the cells to be doing as much as they can do, really. So actually, to do this, I think we would have to culture them still for the 12 days, but perhaps have a lesser volume. But what the conclusion of this one, and I don't really have a explanation for it, so I can say what it isn't. What it is, it's the chilling seems to just boost the proliferation of these encapsulated cells. I can't say is it an effect that's happened to the cells or an effect that happened to the alginate. I tried to do some tests, but they were inconclusive. But at least for encapsulated systems or encapsulated Hep G2 cells we were using here, certainly that if we just have the sample, we simply put them on ice for 45 minutes and then culture them, we can get double the viable cell number. Which I called cryoanaptic C because when I was writing this in the manuscript, it was very difficult, to sort of very tedious when we chill them to explain it every single time. And I'm engaged to a Greek, so I thought I'd make up a Greek word compressor. So I'll just sort of conclude that. So if we chill the cells to below 10 degrees is what I determined was sort of the temperature below which this happened. We can double the viable cell number without really doing any extra effort. This will make the artificial liver device much more economical because you can, say if you're still culturing the 2 litres, you can then just half that and you'll have 2 artificial liver systems as opposed to 1 artificial liver systems. And it has quite a lot of applications to other encapsulated systems, and perhaps if it's a cellular effect to many cells, it still needs to be determined if it is something happening to the cell or something happening to the alginates. But I haven't actually found any evidence of this being reported in any mammalian cell lines. I did quite a big literature search, but most of the things looked either extended culture at low temperatures, which is not what we're doing, or just looked at viability day 1, day 2, day 3 post-treatment, which they reported was chilling was bad, but that's the same as I saw, but when we went to day 12 it was actually the opposite. So I'll just quickly summarise sort of everything I've said today and then open up to questions. So the 2.3 litre biomass, we can sort of prove it can be cryopreserved, and this was sort of the largest volume we could find of mammalian cells that was done in a single cassette, which is quite good. It means we can then actually prove that we can deliver this device logistically to hospital, which is almost important going it in the first place. And then also, the second effect I found sort of almost going on from this was that if we just chill these cells, we seem to have a great boost in the proliferation, which was rather unexpected, but that will make the device much cheaper, more economical to produce, and may have wide applications to other areas. So I'd like to thank you for your time. I'd like to thank John Morris and Barry Fuller, who are here, who are my supervisors, and also Claire Selden, who's another of my UCL supervisors, and in the Medical Research Council for funding the work of my PhD. And thank you all for your attention today.